So today we will try to finish, if we possible, chapter 31. Okay. So remember, in chapter 31 we introduced the self-inductance, and we said if you have a circuit, okay, if you have a circuit with even if there is no inductor and a current is passing through the circuit, when you switch on or you close the switch, the current induces a magnetic field. This magnetic field changes the flux in the circuit, and so it will produce an EMF opposed to the change. And we said that is the self-induced or the back EMF or self-induced EMF. And we said it's equal to minus L, the derivative of the current with respect of time. Okay, so minus L di dt. Okay, and if you put a solenoid like this one with n loops, the induced EMF is actually equal to minus n number of turns, the derivative of the flux with respect of time, which is also equal minus L di dt. Remember, L is the inductance, and so from this we determine that the inductance is equal to the flux linkage, which is n times the flux of the magnetic field through a single coil loop divided by the current. So the flux linkage is n times phi and divided by the current I, and we said the unit of the inductance is Henry. Okay. So we also derived the equation for the inductance of a solenoid, and we said it's equal to a mu 0 n squared, small n meaning the number of turns per unit length, times L, the length of the solenoid, times the cross-sectional area of the solenoid. So in this case, L times A is the volume. So even if the solenoid is rectangular, we can use the same equation, except now the area will be an area of a rectangle. Okay? So this is where we stopped, I think, and this is what we did. We stopped at yesterday. So let me go to the presentation mode. Okay. So we started looking at what happens if you have a circuit that has a battery, a resistor, and an inductor, okay, or a solenoid. Okay, so this is, we refer to solenoids as inductors in a circuit. Okay, so if we have a switch S1 and S2, and if at time t equal to 0, we close switch S1, we can analyze the circuit using Kirchhoff voltage law. So we can use this loop, for example, and we write Kirchhoff's loop equation. So here, if you go from the negative terminal through the battery, you have the battery voltage. Then you go, let's assume this is the current I, and you go through the resistance R. This is minus IR. Then you go through the inductor. And in this case, the potential is going to be minus L di dt. Okay, and all of this is equal to 0. So you have completed the loop. We can solve this equation by playing some mathematical trick. We said we can let X is equal the EMF divided by R minus the current, and hence the derivative of X is minus di. And we can rewrite this equation in this form. Okay, so this is again a partial differential equation, or a differential equation that we can solve. Okay, so if we integrate, so if we rearrange the terms and we perform the integration, we obtain the integral of 1 over x dx is equal minus r over L, the integral of dt, and we can the integral of 1 over x is log of x, so we obtain log of x over x0 is minus r over lt. If we take exponential of both sides, then we get, this is the solution. And now we can determine the current, we can determine current from here. Okay, so this becomes, the current becomes equal to E over R, or epsilon over R, the EMF divided by R, times 1 minus exponential minus RT over L. So this is of the same, so we can write this I is E over R, 1 exponential minus T over tau, okay, where tau in this case is equal L over R, so the time constant. Remember, we dealt with a similar equation when we had a capacitor charging. We wrote for capacitor charging, we wrote Q is equal to epsilon over C, is it? C, so yeah, I think this is what we did, 1 exponential minus T over tau. So this is what we had for a capacitor. So this is an equation that is of the same mathematical form. So if we plot it versus time, okay, this is what we get. So if we plot it, we get it starts at 0. Okay, the current starts at 0 through the inductor and the resistor, and then it increases exponentially. And when t becomes very large, it asymptotes to this maximum value. So this is the I max. You can say this is I max if you want. That's the maximum current that it can reach in steady state, or when t tends to infinity. The time constant of this exponential rise is L over R, okay, and it's also in units of in units of seconds. Okay, now you can see also the time when t is equal to tau, the current reaches 0.63 or 63% of the maximum value, and this is I max, this is I max or I steady state, and so if you go to 2 tau, it will be 95%, 3 tau, and so on. So as the time increases and tends to infinity, the current asymptotes to E over R, which is the battery voltage divided by the resistance. Okay, so you can see that the current does not jump suddenly when you close the switch; it raises exponentially. Yeah? So this is due to the Faraday's effect, or the back-induced EMF in the solenoid or in the inductor. Okay, so as t approaches infinity, you can see that in this case di dt tends to 0, and we obtain so in this case you can see that as if the inductor is disappearing, so it becomes like just a connector, or we can say in steady state the inductor behaves like a short. It's like just a conductor, and we can see that the current is just equal to the battery voltage divided by resistance. So the at t equal to infinity, in steady state, you can draw the circuit becomes just like a resistance, and that's it, as if the inductor is not there. All right. Well, since I mentioned this, I might as well say at t equal to 0. Remember, for capacitors, we said a capacitor at time t equal to 0 behaves like a what? An open or a short? It's like a wire. It's like a short for a capacitor. Here it's the opposite. For the inductor, at time t equal to 0, it behaves like an open circuit. So there is, because actually the current is 0, so there is no current at time t equal to 0. The inductor behaves like an open circuit, as if there is no connection. At time t goes to infinity, the inductor behaves like just a connector. It's like a short. So at t equal to 0, it's open, and at t equals to infinity, it's like a short or a connector. Okay, so this is the current. If we take the derivative of the current, we get this is the derivative of the current. It's E over L exponential minus t over tau, and so if you multiply it by L, you get the potential of the inductor, and this is, remember, this is L di dt. Okay, so if we get this, we get E exponential minus t over tau. So this is the voltage across the inductor, while the voltage across the resistor is just Ri. So it's going to be minus t over tau. Okay, so this is the derivative of the current. Here we're just plotting it, and okay, so the result shows that the time rate of change of the current is maximum, or E over L at t equal to 0, and falls off exponentially to 0 with a time constant equal to tau, L over R. Okay, so these are the resistor voltages. VR is equal Ri. Okay, so this is how the voltage, if you measure the voltage through the resistor, it will, as you close the switch, it will rise exponentially. And so here, this is 10 volt battery here. Okay, and if you take the you determine the voltage across the inductor, it's L di dt, and so when you take the derivative of the current, you get, this is the expression for the voltage across the inductor. So it's an exponential decay. So while on the voltage across the resistor is raising exponentially, the voltage across the inductor is decaying exponentially. So now we can summarize. Right. Okay, so the current rises exponentially, and its maximum value is E over R, and the voltage across the inductor decays exponentially, and it's equal to the EMF of the battery, exponential minus t over tau, and the voltage across the resistor, you can see it rises exponentially. So this is to remember, we did the same thing when we did charging of the capacitor. This is not charging, we are not charging here. Here we are energizing this inductor, and basically we are storing energy in the inductor in a form of a current. And you will see that if we switch the S2 to position B, there will be a current that will flow through a resistor. So let me, okay, so now this is what we're doing. So after we have energized the inductor, okay, now we switch the S2 to position B, and we observe what happens. Okay, so let's assume the current is flowing in the same direction. Well, let's do some reasoning. Okay, now when you switch the switch S2 to position B, so originally you had a certain current, which is E over N, maximum current. Okay, suddenly when you disconnect from the battery, it's going to try to decrease. Okay, so the current is going to try to decrease. Okay, so the flux through the inductor is in this direction, not the induced flux, the flux with the current. It's in this direction down, and it's decreasing. So the EMF will try to oppose that, okay, and it will oppose this. So the EMF actually, the induced EMF, E induced, is going to oppose the change. So it will generate a current that will still flow in this direction, and we can write Kirchhoff's loop equation. Okay, so we can write Kirchhoff's loop equation. So this is, well, let's take it counterclockwise so that we avoid. So if we write it in the, Kirchhoff's loop equation, it's going to be plus IR, because we're going up in the direction opposed to the current direction. And now we're going from the negative to the positive polarity. So we're going to plus L di dt. So again, this is a differential equation, very similar to what we had earlier. We just and we can play the same mathematical trick, and we can obtain the solution. And you can verify if you plug this here, it will give us 0 for the current. So we get the current now is decaying exponentially. Okay, so it starts at the maximum current we had earlier, which is epsilon over r, and then it decays with the same time constant tau. So again, tau is L over r. So this is now exponential decaying current. So like the capacitor, in the capacitor we stored energy in the electric field of the capacitor, and when we disconnected from the battery, we had the voltage was going from the capacitor through the resistor, so there was an exponential decay of the voltage. Here, the energy is stored in the magnetic field of the inductor, and now it's the current that is decaying exponentially. Yeah? So we can see that this current here is going to be flowing through the resistor, and it decays exponentially. So it's as if it's not charging, but energizing the inductor, storing energy in the inductor, and even after we connect the battery, we have a decay, decaying current through the resistor. So this is very nice because we can store energy not only in the capacitor, we can also store it in an inductor, and we can use it in certain applications. Okay. So if we draw all of the variables like we did earlier, this is now for the inductor energizing or producing a current, decaying current through the resistor. So this is the current. Okay. If you want to determine the inductor voltage, V is equal L di dt. This is L di dt. So if you take the derivative of the current, you get VL is going to be minus E exponential minus RT over L. Okay, so you can see the voltage starts negative if you're measuring with your voltmeter like this. So this is the positive side of the voltmeter, this is the negative side of the voltmeter. So you will be measuring a negative voltage, and it will rise exponentially to 0. Okay, so it will asymptote when t goes to infinity to 0, but it will start at a negative value. The voltage through the inductor, through the resistor, and this one is just equal Ri. So if you multiply the current times R, you get the battery voltage, the EMF, epsilon exponential minus RT over L. So very similar to what we had before of discharging of capacitor. Remember, in discharging of the capacitor, this was the shape of the charge. Q decayed exponentially from the maximum of the value, and it decayed exponentially to 0. In this case, the decay is not of the charge but of the current. So the but you see the behavior is very similar. Okay, so let me start the Kahoot for this one, and let's join the Kahoot, chapter 31, and play chapter 31 lecture. Okay, so join the Kahoot at the following pin. Okay, 736-1324. Please join everybody. Okay, so while everybody is joining, let me start the Kahoot. So let me magnify this. All right, so I'll give you a minute. I will read it. Consider the circuit in the figure with S1 open and S2 at position A. Okay, switch S1 is now thrown closed. So you close switch S1. At the instant it is closed, across which circuit element is the voltage equal to the EMF of the battery? Is it across the resistor, the inductor, or both the inductor and resistor? All right, so I'll give you half a minute to think about this. Huh? The code. The code is 7361324. 7361324. Okay. So think about it. Ready? If you're ready, raise your hand. Huh? Only Ibrahim. Yes? Ready? I want everybody to be on board. Don't worry about the quiz, ya Jama'ah. Huh? Okay? Alright, so let me start the Kahoot and okay, choose between A, B, or C. يلا يا جماعة يلا. Five seconds. Okay, well, good. 13 correct answers and 18 incorrect answers. All right, so let's see what's happening here. Okay, so here at the instant it is closed at t equal to 0. What did we say about the inductor? How does it behave when t is equal to 0? Huh? No, at t equal to 0. It's open. Huh? We said at t equal to 0, when you just close the switch, the current is 0, and remember the inductor is going to be opposed to the current. It does not want to see any change in the flux. So it will act like an open, the opposite of the capacitor. So it acts like an open, so the equivalent circuit that we can get is like this. So this is the battery, and we have a resistor, and this is open now, as if there is nothing. So across which element you will find that the voltage is equal to the battery voltage? If you put a voltmeter here, what will you measure? What's the voltage it will measure? You measure the voltage of the battery, because there is no current flowing anymore. There is no current flowing, so there is no change in potential across this resistor. So if you put a voltmeter across here, so the inductor is like an open, you will be measuring the same potential as that of the battery, because the inductor at time equal to 0, when you close the switch, acts like an open, as if it's not there. So the correct answer is B. All right, next question. Let's go back. All right, so here's the results. Okay, so this is another question. After a very long time, across which circuit element is the voltage equal to the EMF of the battery? Across the resistor, the inductor, or both the inductor and the resistor? I'll give you 20 seconds to think about this. Discuss it with your neighbor. If you don't have a neighbor, try to make one. or try to join a neighbor. Okay, so make a decision, A, B, or C. Oops, sorry, what happened? Okay, so this is actually the next scout. There was no, all right, never mind. So what was your answer? Who says A? This is the previous one, huh? Who says, so this is the one, huh? Who says A? Raise your hand. Okay. Who says B, the inductor? C. Okay, so clearly A is the correct answer. So what did we say about the inductor in steady state? In steady state, it acts like a short, like a connector, opposite of the capacitor. So let's draw the circuit now. So if we draw the circuit, it becomes a resistor, and as if the inductor is just a connector. It acts like a short. So where do you measure the same voltage as? So if you measure the voltage between these 2 points, you are also measuring the voltage across the battery. So the resistor. In this case, if you measure with a voltmeter, the voltage across this resistor here, since this is like a connector, so as if you are measuring it across the battery, you will be measuring the same voltage as the battery. واضح شباب؟ So an inductor acts the capacitor. The capacitor at time equal to 0, it acts like a short. And time equals to infinity in steady state, it acts like a connector. It acts like an open circuit. There is no current flowing through it. The inductor is the opposite. At time equal to 0, it acts like an open. There is no current flowing through it. Current is 0. But at time t goes to infinity, the inductor behaves like a connector, like a short. All right, so let's do some problem solving. Consider the circuit in this figure. So same circuit. Suppose the circuit element has a following value: 12 volt battery, 6 ohm resistor, and 30 millihenry inductor. Find the time constant of the circuit. That's easy. Time constant is L over R. So it's 30 10 to the minus 3 divided by the resistance, which is 6 ohms. Okay? So that's 5 10 minus 3, yeah? Or 5 milliseconds. Okay? Switch S2 is at the position A, and switch S1 is thrown closed at time t equal to 0. So we close the switch S1 at t equal to 0. Calculate the current in the circuit at t equals to 2 milliseconds. So we have the equation for the current. We said it's epsilon over R, 1 minus t over tau, which is a time constant. So this is going to be equal to 2 milliseconds. We are evaluating it at 2 milliseconds. So we just replace, this is 12 divided by R, which is 6, 1 exponential minus t. So this is 2 milliseconds. So 2 10 to the minus 3 divided by tau, which is 5 10 to the minus 3. So 10 to the minus 3 cancels out, and you can get what is the current at t equal to 2 milliseconds. Compare the potential difference across the resistor with that of the inductor. Okay, so across the resistor, it's equal Ri, which is epsilon 1 exponential minus t over tau. Okay, across the inductor, this is the resistor, V across the resistor. V across the inductor is L di dt, and we said that this is going to be equal to epsilon exponential minus t over tau. So if you plot them, one is rising, the voltage across the resistor is rising exponentially, and the voltage across the, so this is VR, and across the inductor it's decaying exponentially. Okay, so and both of them are at the same value, starting at so this is the voltage across to the inductor. Okay, so you can use these equations to calculate the voltage across the resistor or the inductor at any time using the equation. All right, so this is what we get. The current is 0.659 amps. This is VR and VL, and you can evaluate them at 2 milliseconds, and you get the values. So you can see the potential difference across the inductor is decaying exponentially. The potential difference across the resistor is increasing exponentially. Okay, here is another example from another book. Okay, here we have a circuit that contains 3 identical resistors with 9 ohm and 2 identical inductors, and each one has an inductance of 2 millihenries, and an ideal battery of epsilon 18 volts, and the EMF is 18 volts. What is the current I through the battery just after the switch is closed? I'll give you 20 seconds to determine that. What is the current through the battery just after the switch is closed? This should jump. Yalla, who? At time t equal to 0, what is the current through the battery? Anybody? Yes. Yes. It's just the battery voltage over R. What did we say about the inductors at time equal t equal to 0? They behave like what? Open. So as if it's not existing. So this is not there. This is not there. So this resistor is not connected. This resistor is not connected. So you just have the circuit. It's a battery and a resistance R. And so the current is just going to be the EMF voltage divided by R. Okay? The next question, what is the current I through the battery long after the switch has been closed in steady state? Yes. Yes. And what's R equivalent? Correct. Electrical engineer? Huh? Good. Thanks. All right. So here, so let me repeat. So when at t equal to 0, these are open. So you have a battery, and this is open. This resistance is open. This resistance is connected, and this resistance is open. There is no connection here. So you obtain the current is just equal to the EMF over R. At t equals to infinity, now these are shorts. The inductor behaves like a connector. So this becomes like this, and this becomes like this. So you have R, R, and R. Okay? So what is R equivalent? 1 over R equivalent is 1 over R plus 1 over R plus 1 over R. That's 3 over R. So R equivalent is R over 3. Okay? And so you can write that the equivalent circuit is just like a battery, and R equivalent, and you obtain the current is just equal the EMF of the battery divided by the R equivalent, which is R over 3. So actually, if you are analyzing a circuit that has inductors and you're told t equal to 0, immediately t equal to 0, it acts like an open. So as if they are not there. So it simplifies your circuit. Same thing, if you are asked at steady state, where t is going to infinity, now the inductors is like a short. It's like just a simple connector. It becomes just a simple resistive circuit. Same thing for the capacitor, but it's the opposite. The capacitor at t equal to infinity is like open, and at time t equal to 0, it acts like a short. So you can easily simplify your circuit, even if it has a capacitor and inductor, especially if you're told at t equal to 0 or t equals to infinity. Okay, so here this is a solenoid that has an inductance of 53 millihenries and an inductance of 0.35 ohms. Okay, if the solenoid is connected to a battery, how long will the current take to reach half of its final equilibrium value? So here, the solenoid has a resistance itself, but we can write that the equivalent circuit is the same. So this is the resistance of the solenoid, this is the inductance of the solenoid. Okay, so R and L, and again it's the same equation that we have for current. It's 1 exponential minus t over tau, which is L over R, and we are asked how long it will take for it to reach the half the final equilibrium. The final equilibrium value is maximum, which is epsilon over R. So when it reaches epsilon over R divided by 2, okay, so the maximum current cancels out, and we obtain 1 minus exponential minus t over tau is just equal 1/2. Okay, so we can rearrange this. This is exponential minus t over tau is equal to 1/2, and we take log of both sides, so we get minus t over tau is log of 1/2, or we can write t is log of 2 times tau. Remember, log of 1/2 is minus log of 2, so this is minus log of 2, and so the time t is going to be L over R times log of 2. So you can replace the values and calculate how long it will how long it takes for the current to reach the half of the maximum value. It can be 1/3, 1/4. So this is a very common question. It's like capacitor circuit. In the quiz you had a very similar question. So, all right. All right, let me go to the energy equation, and this is interesting. Let me go to presentation mode for this. Okay, so remember we had written the loop equation for this circuit, and we said it's E minus Ri minus L di dt is equal to 0. If we multiply this equation by the current flowing through the circuit, we obtain the power. So notice this is the power through the battery, this is the power through the resistor, and this is actually the power through the inductor. Okay, so this element here, Li di dt, is equal the change in energy across the inductor with respect of time. Okay, so we can say the power that is generated by the battery, part of it is dissipated in thermal heat through the resistor, and thermal heat is usually lost, and part of it is actually stored in the magnetic field of the inductor. Okay, and so L di dt, Li times di dt is the rate at which energy is being stored in the inductor associated with the magnetic field of the inductor. Okay, so we can write this here, that the derivative of the energy stored in the inductor with respect of time, which is the power, is equal Li di dt, and we can integrate both sides to determine the energy in the inductor. If we integrate, it's a simple integral, so it's going to be the integral L times the integral from 0 to I of Li di, and when we do that we find that this is equal to 1/2 Li squared. The energy stored in an inductor is equal 1/2 Li squared. Remember, what did we have the energy stored in a capacitor? Remember, what was it? it was the energy stored in the capacitor. So this is an electric field of the capacitor, was 1/2 C delta V squared. Here, the energy stored in the inductor is 1/2 L I squared. So if I ask you to determine what is the equation, let's assume here you can replace I squared. So this is going to be, if you want it versus time, UB is going to be 1/2 L. I squared is epsilon over R squared times 1 minus exponential minus T over tau squared. So you can actually, when the inductor is being energized, is storing energy, you can determine what is the energy at any time, because you have an expression of the current, and since the energy is 1/2 Li squared, okay? What is the maximum energy that an inductor can store in this case? So the maximum current, what do we say? I max is equal E over R, epsilon over R. So we can say that the maximum energy that we can store is going to be 1/2 L times E squared over R squared, which is yes. So which is 1/2 L I max squared. So the inductor can store energy in the magnetic field because the inductor has a magnetic field when the current is flowing through it. Okay, so this is very nice. Now let's take a solenoid, okay, and try to determine the energy and the energy density of the solenoid. Remember, we derived earlier or previous lecture that the inductor inductance of a solenoid is mu0 n squared times the volume. N is the number of turns per unit length. Okay, and so if we want to determine u, we said it's 1/2 Li squared. Okay, so this is going to be right. So here, yeah, 1/2 Li squared. So we can replace L. Okay, and yes. Okay, so here it's going to be 1/2 mu0 n squared times the volume times I squared. Okay, now if we all right, so if we determine the energy density U over V, this is going to be 1/2 mu0 n squared I squared. Okay, and so what was this 1/2 mu0 n squared I squared? I wanted to get to something else here, but let's see. So yeah, I forgot. So I wanted to replace B. B is mu0 n I. Okay, so the energy is 1/2 Li squared. Okay, and I we can obtain the current I. It's B over mu0 n. So if you plug into this equation, this is what you obtain. So now it's a function of a magnetic field in the solenoid. It's B squared divided by 2 epsilon 0, 2 mu0 times the volume of the solenoid. Remember, this is volume, which is the area times the length, cross-sectional area. The energy density, now if you divide the energy by the volume of the solenoid, you obtain B squared, 1/2 B squared over mu0. So the energy density in the solenoid is 1/2 B squared over mu0, which is very similar to what we have seen before. Remember, we said the energy density of a capacitor, what was it? Was 1/2 epsilon 0 E squared. Remember, this is, we said, this is the energy density of any electric field. It does not have to be a capacitor. If you have electric field in space, you can determine the energy density of that electric field by multiplying by 1/2 epsilon 0 E squared. And if you have a dielectric, you have to add the kappa, the dielectric constant. You have to write kappa here, but let's assume it's in air. Okay, so this is a very similar equation It is 1/2 b squared divided by mu 0. And this is valid not only for a solenoid, for any magnetic field in space. So if you have an expression of a magnetic field in space and you want to determine what is the energy per unit volume, energy density, you just plug 1/2 b squared divided by mu 0. So this is, remember, this is important because it's not only connected to a solenoid, although this expression was derived for a special case of a solenoid, it is valid for any region in space in which a magnetic field exists. So this is very important property. So the electric field has a property of storing energy. Like in a capacitor, you can store energy and use it. Also, the magnetic field has the capability of storing energy and being used in a circuit. Remember, it was giving us a current through the resistor. Okay, this similar equation is very similar to the energy per unit volume for an electric field. For any electric field is 1/2 epsilon 0 E squared. Okay, so now we go to the next checkpoint. All right, still have plenty of time. So let me end the show, discard, and let's go to the Kahoot. All right, so this is the next Kahoot. Okay, so the table lists the number of turns per unit length, current, and cross-sectional area of 3 solenoids. Rank the solenoids according to the magnetic energy density within them, greatest first. So you have solenoid A has 2N1 turns per unit length, current I, and an area 2 capital A1. B has N1 turns, 2I1 for the current, and C and for the area A1, and so on. So I want you to rank the solenoids according to the magnetic energy density within them. Magnetic energy density. 1 minute for this one. If you want the pin, 736-134-1324. Discuss with your neighbors. It's okay, I like to see some noise. Discuss it on the right. Ready? Who's ready? Raise your hand. Who's ready? Nobody yet, huh? Okay. يلا يا جماعة, this is a simple one, huh? So it's 1/2 mu 1/2 b squared over mu 0, huh? Okay, so let me start for the sake of time. Okay, so choose between A, B, C, or D. Okay, all right, so only a minority, 7, huh? 7 got it right. Okay, let's see. I don't know if it all right, so here we just use the equation. This is not something you can just figure out without writing the equation, huh? So what did we say? We said the energy density is 1/2 b squared over mu 0. What is b for a solenoid? B is mu 0 and I. So this is going to be 1/2 mu 0 and I squared divided by mu 0. So it becomes 1/2 mu 0 times n squared times I squared. Notice the cross-section area does not play any role in this. So what is for A? For A, it's 1/2 mu 0 2n1 squared times I1 squared. For mu B, it's 1/2 mu 0 n1 squared 2I1 squared. So this is here, we can write this is 2 mu 0 n1 squared I1 squared. This is going to be also same thing, 2 mu 0 ni squared I1 squared. UC is going to be 1/2 mu 0 n1 squared and I1 squared. So clearly you see that mu A is equal mu B, UA is equal UB is equal and is larger than C. So the energy density does not depend on the cross-sectional area of the solenoid. It only depends on N, the number of turns per unit length, and the current through the inductor. All right? So let me skip this one and here. All right. Okay. What happens to the energy in an inductor? So consider again the RL circuit shown in the figure with the switch S2 as position A and the current having reached a steady state value, which is the EMF battery divided by the resistance. Okay. When S2 is thrown to position B, the current in the right-hand loop decays exponentially with the time according to the equation. I is equal epsilon over R exponential minus T over tau. Show that all the energy initially stored in the magnetic field in the inductor appears as internal energy in the resistor as the current decays to 0. So what we want to do, we want to prove that all of the energy that is stored in the inductor is actually dissipated through the current. Remember, the power through the current is Ri squared. And the power, this is dE dt, isn't it? This is the rate of energy change with respect of time. And we want to determine the total energy. Okay? So from this equation, we can write that dE is equal Ri squared dt. Okay? Now, let me replace. So this is Ri squared. So if I replace I squared, that's epsilon squared over R exponential minus 2t over tau. So 2t over tau, or let me minus 2 RT over L, okay, dt. This is the partial change in energy. So if I want to determine the total energy, I have to integrate dE from 0 time equal to 0 to infinity. Okay, so this is going to be the integral of epsilon squared R, okay, exponential minus 2 RT over L dt from 0 to infinity. This is a total energy. Okay, so let's try to evaluate this integral. Okay, so we have E squared over R. Okay, and we have to multiply by minus R, is it? L over R. Okay, so here we're going to divide by R over L. Okay, and yes, so this will be L over R here. Okay, exponential and minus RT over L, and evaluated between 0 and infinity. Okay. So here, if we do that, exponential minus infinity is what? 0. Exponential 0 is 1. So this becomes L over R, not I, L over R squared E squared. All right. What did we say about the energy? U is 1/2 Li squared. I should have left 1/2 L I squared, or I squared over L, is it? So we had 1/2 Li squared. So normally, there is, okay. So normally the energy is 1/2 Li squared. What is I? It's E squared over R squared. هكا ولا? This is the energy that is stored at the inductor. Okay. So where did I lose the 1/2? Oh yeah, I forgot. There is a 2 here. So there is a 2 here. Okay. So notice that this is the same as the energy that is stored in the inductor. So all of the energy that we had in the inductor, which was stored in the magnetic field of the inductor, was 1/2 L epsilon squared divided by R squared. When you switch the S2 to position B, it will all of that energy is going to be transferred to the resistor. So if you integrate the energy over time from 0 to infinity, you will obtain the total energy that was in the inductor. Okay.